There are many natural phenomena around us which make us wonder why they happened. For example, after rain, you may have seen that rain droplets stick to the leaves. Why? You may have also noticed that plastic wrap sticks to itself. Again, you may have wondered why. Also, have you ever wondered why olive oil and water do not mix with each other? The answer to many of these phenomena can be explained by understanding how molecules interact at molecular level. In this section, we will examine molecular polarity. Uh, it is an important characteristic of molecule, and it's the one which determines how molecules interact with each other. In previous chapter, we learned that covalent bonds are formed when nonmetals share electrons. For example, if we have a covalent molecule such as HCl, the covalent bond is formed when one electron from hydrogen and another electron from chlorine is shared between them, and chlorine gets to keep the remaining 6, and these shared electrons they form covalent bond. So these electrons which are shared to form a covalent bond are known as bonding electrons. In bonding electrons, one electron belongs to one atom and the other electron belongs to another atom, and technically both of these electrons remain in the middle of two molecules, two atoms, and both of these atoms complete their duets or octets. Upon studying the covalent bond, it has been found that bonding electrons are not necessarily shared equally between two atoms. One atom is often better able than the other atom to attract electrons towards its nucleus, as shown in the case of oxygen and hydrogen covalent bond. As we can see that the shared bonding electron are more towards the oxygen nucleus. The atom's ability to attract the shared pair of electrons, such as oxygen is doing here, uh, this ability of atoms to attract the shared pair of electron is known as electronegativity. So we can define electronegativity as ability of an atom when part of the covalent bond to draw electron towards its nucleus. All elements in periodic table have electronegativity values. Higher electronegativity value means that that particular atom has more tendency or more ability to attract the shared pair of electrons towards its nucleus. This table shows us the electronegativity values of main group elements. The values of electronegativity varies from 0 to 4. The highest value belongs to fluorine and it has value of 4.0. So fluorine has the highest electronegativity value. In other words, whenever fluorine is bonded covalently to another atom, it has the highest tendency or ability to attract the bonding electrons towards its nucleus. Oxygen has the second highest value of electronegativity, and nitrogen and chlorine they have the third highest value. One trend we can see here is that on this side of the periodic table we have highest value of electronegativity. If we go down the group, electronegativity value decrease, and if we move from the right side of periodic table to the left side of periodic table, even then the electronegativity value decrease. Trends in electronegativity are seen across the elements on the periodic table. Electronegativity decreases from top to bottom So therefore, within a group, the element with the smallest atomic number will have the highest electronegativity. As we go down the group, the value of electronegativity will decrease. Valence electrons, which are the electrons in the outermost energy level of an atom, determine the electronegativity value of an element. The closer the valence electrons are to the positively charged nucleus, the greater will be the electronegativity value of that atom. Thus, within a group, electronegativity decreases from top of the group because top of the group has smaller atoms, and smaller atom means that their uh, valence electrons are closer to the nucleus. At the bottom of the group, the atom size increases, so those are bigger atoms. So bigger atom means that their valence electrons are farther away from the nucleus, so therefore the attraction towards the nucleus is less. Within a period such as period 2a, electronegativity increases from left to right as a result of increasing number of protons in the nucleus. For example, fluorine is more electronegative than oxygen, and oxygen is more electronegative than nitrogen, and so on. When covalent bonds are formed, the difference in electronegativity between two atoms that form a covalent bond determine whether the bond is polar or non-polar. Let me explain with the help of an example. Imagine that we have two different covalent molecules. One is HF, the other one is H2. HF is formed when hydrogen and fluorine shares electron and form a covalent bond. Now, this is the bonding electron pair. So one of the electron belongs to hydrogen, the other one belongs to fluorine. Similarly, if H2 molecule is formed, in that case, hydrogen shares electron with another hydrogen. Now we know that atoms have different tendencies or ability to attract the shared electron, the bonding electron. In case of hydrogen molecule, both side of the molecule has hydrogen atom, so they are same atom, so therefore their ability to pull or attract the shared electron is equal. So in that case, both of these atoms, as shown here, are pulling the shared pair with same number of force. Hence, this shared pair remains in the middle, right in the middle. So in this case, the electrons do not move, so they are exactly in the middle. However, situation is different in case of HF. This picture shows HCl, but the logic is still the same. So Cl has a high electronegativity. So therefore it means chlorine has more power or more ability to attract the electrons. So what will happen, that chlorine will pull these electrons towards itself, and hydrogen, although one of the electron belong to hydrogen, but hydrogen will lose that electron partially because chlorine is able to pull that electron away from hydrogen. So that's why hydrogen is losing it. In this case, in the other case, none of those two hydrogens are losing an electron because they are pulling with the same amount of electronegativity. Uh, so therefore, although our molecule Lewis structure looks like that, but actually what happens is this molecule should look something like that, where fluorine pulled a hydrogen electron away from hydrogen. So hydrogen has lost its electron partially, not completely, but it's away from it, so it feels like it has lost it. We know that electrons are negatively charged. If fluorine has gained the electron because it pulled it away, therefore fluorine will become negatively charged because it has gained or pulled one electron away from hydrogen. However, fluorine, although it has pulled it away, but it did not completely took it apart from the hydrogen. Hydrogen is still nearby. So it's not a complete negative charge, it's a partial negative charge, and we represent partial negative charge with this symbol. So this is called delta. It's a Greek letter. It's called delta negative. Now, because fluorine has gained the electron, therefore hydrogen must have lost some of that electron. So therefore hydrogen gets a positive charge. So again, it's called a delta positive because it's not completely lost it. So there will be a partial positive charge on hydrogen and partial negative charge on fluorine. Similarly, in this case also, this hydrogen, poor hydrogen, will get a partial positive charge because it has lost part of its electron, and chlorine will get partial negative charge. Now the charges are created whenever difference in electronegativity moves the electron closer to one atom over the other. So this difference in electronegativity value has created uh, charges on each atom of that molecule. So this creation of charge led to formation of a dipole. Dipole is a force which runs from the positive side of the molecule to the negative side. It is represented by a arrow. It's kind of like a force. It's running through the positive charge to negative charge. And whenever a bond has a dipole in it, for example, in case of HF, again, we will have a dipole running from here to here. Uh, so any bond which has a dipole, those bonds are known as polar bonds, polar covalent bonds. And the bonds which do not have dipole, such as hydrogen, H2, those bonds are called nonpolar bonds. So as discussed in previous slide, due to uh, the difference in electronegativity values, uneven electron distribution will happen whenever a high electronegative element is covalently bonded to low electronegativity element. So this uneven distribution of electron because will lead to formation of partial charges where negative charge will form on the high electronegativity element and positive charge will form on the low electronegativity element. So separation of partial charges is known as a dipole. And remember, dipole is represented by an arrow where the uh, tip of the arrow points towards the negative charge and the base of the arrow points towards the positive charge. A covalent bond with dipole is known as a polar covalent bond or simply polar bond. A polar covalent bond is often depicted by a arrow running from the positive charge to the negative charge. The covalent bonds formed between two nonmetal atoms that have same or very similar electronegativity values are classified as nonpolar bonds. For example, bond between hydrogen and hydrogen, that would be a nonpolar. Similarly, bond between a fluorine and another fluorine, that would also be a nonpolar, because both fluorine, although they are the highest electronegativity element, but both are equally stronger. Even the bond between elements who have similar electronegativity values, such as carbon and hydrogen. So in this case also, carbon electronegativity value is 2.5 and hydrogen is 2.1. So this is pretty close. So even in that case, the bond um, is nonpolar. In nonpolar covalent bonds, electrons are evenly distributed. Nonpolar covalent bonds do not have partial charges, and therefore they do not have bond dipoles. Nonpolar bonds are found in diatomic elements such as hydrogen, nitrogen, oxygen, chlorine, fluorine, and they are also found in carbon-carbon and carbon-hydrogen bonds of hydrocarbons and many other compounds which contain only carbon and hydrogen. Propane is an example of a molecule which contains a non-polar bond. As we learned in previous slide, that carbon and hydrogen have almost similar electronegativity. Therefore, these shared electrons remain right in the middle. Hence, they do not have any partial charges. So therefore, there are no dipoles. So therefore, uh, this molecule has non-polar bonds only. In previous chapter, we learned about ionic bonds as well as covalent bonds. And in this chapter, we learned that covalent bonds can be polar covalent or they can be non-polar covalent bonds. We have learned that these three kinds of bonds are part of a continuum that spans from non-polar covalent bond from one end all the way up to ionic bond at the other end. Non-polar bonds have equally shared electrons uh, between them, because the difference in electronegativity between two atoms is negligible. Let's solve this problem. Place a partial positive charge and partial negative charge on the atoms in these polar bonds. So all of these are polar bonds. We can determine that they are polar by looking at the electronegativity difference between the atoms. Uh, if the difference of electronegativity is anywhere from 0.5 to 2.0, so the bond will be polar. So if the bond is polar, then one side of the bond will have a partial positive charge, the other one will have negative charge, and we need to place those charges. And remember, partial negative charge is always on the atom with higher electronegativity value. So if we look at the periodic table, we'll find that the chlorine has higher electronegativity than hydrogen, so it will have partial negative, hydrogen will have partial positive. And in case if you want to draw the dipole will be this way. Similarly, The negative charge will be on nitrogen, positive charge will be on carbon. Fluorine will have the partial negative, phosphorus will have partial positive, and in all these bonds, direction of dipole will be from left side to right side. In previous slides, we learned that covalent bonds can be polar or non-polar. Now we know that within a molecule, we may have multiple bonds. For example, in case of a methane molecule, we have 4 different covalent bonds. Now, all of these bonds may be polar or may be non-polar. So the resulting effect is that just like bonds may be polar or non-polar, the overall molecule may also be polar or non-polar. In polar molecules, we have a separation of charge within a molecule, and we call that separation of charge a dipole. In contrast, a non-polar molecules have even distribution of electrons, hence there is no separation of charges and therefore no dipole. Both polar and non-polar molecules have very different physical and chemical properties. Polarity differences among molecules are important in biology and biochemistry. For example, the polarity of drug molecule determines whether or not it can cross the blood-brain barrier. We will learn more about the concept of molecular polarity in chapter number 8 when we'll discuss about various mixtures and solutions. In order to determine the polarity of the entire molecule with more than 2 atoms, we must consider polarity of all the bonds together with the molecular geometry of the molecule. Let's look at examples of molecules which can be non-polar. Generally, there are 2 ways in which simple molecules can be non-polar. First is when all the bonds within the molecule are non-polar, then the molecule itself will also be non-polar. For example, methane. In case of methane, it has 4 different carbon and hydrogen bonds. Now carbon electronegativity is 2.5, hydrogen is 2.1, difference is too small. So all of these 4 bonds are non-polar. Now because all the bonds are non-polar, therefore this entire molecule is also non-polar. That is one way a molecule can be non-polar. The second way is that if all the bonds in the molecule are polar and identical and the central atom has no non-bonding electron, in these molecules the identical bond dipoles cancel because of the symmetry within the molecular geometry. For example, linear, trigonal, planar, and tetrahedral molecules are symmetrical. Therefore, the polar bonds will cancel each other out. Let me explain with the help of an example. So, for example, if I have a linear molecule such as carbon dioxide. Now, in this case, the molecule is symmetrical and it has dipole because carbon is 2.5, hydrogen electronegativity is 3.5, and this is partial negative, this is also partial negative, and that's partial positive. So we do have one dipole this way, the other dipole this way. Now because of the symmetry within the molecule, these 2 dipoles cancel each other out and the molecule becomes non-polar. So therefore a molecule with symmetrical geometry and identical polar bonds will also be a nonpolar molecule. Another example is if a molecule has a trigonal planar geometry. Uh, in that case also, for example, BF3. So in this case also, this molecule does have three polar bonds. BF bond is a polar bond. So it has three dipoles, but because the molecule is symmetrical, so these three dipoles cancel each other out, so this molecule will become non-polar. So remember, if all bonds are non-polar, then of course molecule will be non-polar. If your molecule does have polar bonds, then you need to look at the geometry. Three geometries are symmetrical and those geometries are linear. In linear, dipoles will cancel. Second is trigonal planar, and third is tetrahedral. If any of these three geometries are there and your molecule does have identical polar bonds, those polar bonds will cancel each other out and your molecule will again become non-polar. Some examples of non-polar molecule with non-polar bonds are given here. So all the bonds in these molecules are non-polar, hence overall these molecules are also non-polar. As I explained earlier, if your molecule does indeed have a dipole or multiple dipoles, but the geometry of your molecule is symmetrical, those dipoles will cancel each other out, and three symmetrical shapes are the one in which the dipoles cancel each other out, and these shapes are linear, trigonal, planar, and tetrahedral. If your molecule is any of these three cases and it has dipoles, those dipoles will cancel and all of these molecules will again become non-polar. Now, in contrast, a polar molecule can be a molecule which has only one polar bond. For example, there's only one polar bond, so one dipole, nothing to cancel, so this will be polar. Another example is, although it's a symmetrical shape, but there is only one dipole because there's only one polar bond, nothing to cancel on the other side, so therefore this will also be polar. A molecule with non-symmetrical molecular geometry and more than one polar bond will also be polar. For example, bent, it's non-symmetrical, so one dipole going this way, the other dipole going that way, so they don't cancel each other out, they just go right through it, so resulting in the formation of a average dipole in the middle, so this will also be a polar molecule. And finally, a molecule with a symmetrical geometry but non-identical polar bonds. In that case also molecule will be polar. Why? Because these dipoles are non-identical. So CCl dipole is different because the electronegativity values are not the same. So this dipole will not be able to cancel the other dipoles because uh, they are not identical. Remember, only identical dipoles cancel each other out. Hence, in that case also, uh, a molecule will be polar. Let's identify if these molecules are polar or non-polar. In example number one, um, it's a symmetrical molecule with same electronegativity value. So this bond is non-polar and there's only one bond. So hence this molecule is non-polar. In this case, a symmetrical molecule. However, the dipoles are non-identical. So two of the dipoles are carbon and chlorine, whereas the third dipole is between carbon and oxygen. And remember, only the identical dipoles cancel each other out. So therefore, although the molecule is symmetrical, but because the bonds are not identical, so therefore they will not cancel each other out, and this molecule will be polar. There is only one bond, and fluorine has a high electronegativity. Iodine is pretty low, so therefore this molecule will have a single dipole. Any molecule with one dipole will always be polar. Now, although it looks like uh, a plus sign, but remember it's a tetrahedral structure. So tetrahedral structure means actual structure is this way. However, it's an identical molecule with a symmetrical molecule with identical bonds, and tetrahedral is one of the molecule where dipoles cancel each other out. So therefore, although there are four different dipoles which exist here, but all of them are identical and molecule is symmetrical, so they will cancel. So therefore, this molecule will be non-polar. And finally, in this case, both carbon and sulfur has pretty similar electronegativity value, so they don't even have any dipoles. So no dipoles. So no dipoles means uh, uh, why there is no dipole? Because carbon electronegativity is 2.5 and sulfur electronegativity is also 2.5. So difference in electronegativity is 0. So therefore no dipole. No dipole means non-polar molecule.